Hey guys, welcome to Great Learning. Statistics finds itself to be at the heart of any concept involving analysis, pattern matching, and even machine learning. Now, all of these concepts are constantly in the trend, which means that it becomes important for you to stay informed about all the concepts of statistics. This important course on descriptive statistics will help in setting a very strong foundation for you to understand everything you need to know about this somewhat complex domain. It definitely is easier than you might have thought, and this course proves just that, using an ample amount of examples and bite-sized concepts to help you have complete clarity about the same. With that, I know you guys are super excited to get started with this course. Well, what are we waiting for? My name is Anirudh Rao. Let's get started.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleagues, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.
Alright guys, so coming to the agenda of this particular course, we need to understand a lot about descriptive statistics in this course. Now to go on to do that, we have to take a very structured approach and we have to break a lot of things down into very simple pieces, as I mentioned, because things can get really complex if you do not have a structured and an easy understanding in statistics. So to do that, we are going to start out by taking an introduction to statistics. I'm going to give you a couple of examples to actually help you understand statistics better. Once we go on to discuss all of these examples, the next thing you will be curious about after you know what statistics is that, hey, so we are going to need a lot of data for statistics, right? That is something I'm sure you would know even at this moment of time. So if a lot of data is required, how do you work with various types of data that are out there? What are some of these various types of data? How are we bringing it to the world of statistics, and a lot more, right? So we're going to cover all of that. Once you understand the various types of data you're going to be dealing with and understand the various ways of handling these data, you're going to be very curious to take a look at understanding what are some of the various types of statistical analysis that we can go on to perform. Once we understand the various techniques that are out there and in terms of what type of analysis can be performed in what situation, you will have an exposure to understanding what are some of these requirements, what are some of these key concepts that act as a complete foundation for descriptive statistics itself, right? So that is where we are going to take a look at understanding what are some of the various measures of central tendency that are out there. After that, we're going to also be taking a look at some of the various measures of variability, measures of relationship, the concept of skewness, what it is, how it works. In fact, why is skewness so important for us to measure and understand? And at the last, we're going to be taking a look at one very interesting concept called as kurtosis. Now, kurtosis or kurtosis as it's called is a very popular concept in the finances domain. And once you understand one example of why kurtosis is important for us, you will realize that it's not just finances. There are numerous applications out there. In fact, there are many real-world applications being driven right now after performing some analysis through that, right? So we are going to understand everything right from the basics of statistics all the way to understanding complex concepts such as skewness and kurtosis in this course. Well guys, with this, I hope we are clear with the agenda for this particular course. So without further ado, let us dive right into the heart of the topic to have an introduction to understanding statistics. Now, ladies and gentlemen, what is it that first comes into your mind whenever you think about statistics, right? Whenever someone says stats, whenever someone says statistics, I'm sure that you'll have a first train of thought wherein it has to do something with respect to numbers, measuring numbers, understanding the behavior of numbers and all of that, right? Yes, it is considered as a major part of mathematics, but with respect to statistics, we will be discussing and diving right into data data, we're going to be diving right into the metrics, which will give you a lot of clarity about how you can use the data points, right? I'll give you a very short example. In fact, we'll actually discuss 2 examples to give you an idea about statistics. The first story, right? Let's just consider a small story right now. There is a new TV show which is trending, maybe on Amazon Prime, maybe on Netflix. So, of course, if something is trending and it is super popular, you already know this for a fact that the social medias are going to blow up, right? The first is Twitter, the next is probably Facebook, and then everyone on Instagram are going to start talking about it. People in WhatsApp groups are going to start talking about, hey, this is a brand new TV show that came out. I liked this about it. I did not like it. Some say it's just a hype. It's nothing great, right? So there are so many mixed opinions that you might get whenever there's something new, something trending. So what will you do in this particular situation? If it's a case where a new TV show came out, people are raving about it, and now you want to do some sort of analysis. You want to weigh to understand why people are probably rating it very low, or the contrary, why people are rating something very high, right? Of course, you're going to do this. Now, how I do it. If there's a new TV show or if there is a new movie that has come out, the first thing I'll do is I'll probably head to Google. I'll take a look at the various cast members that are out there. I'm going to take a look at the storyline. I'm going to also take a look at genre, of course, right? Now, I love watching documentaries. I love watching comedy movies, comedy TV shows and all of that. So I have a preference, right? I want to see if this new TV show aligns to my requirement. So what do? We go to Google, we take a look at the reviews, and what do? We see the ratings of it, right? Now, what do you mean by seeing ratings? Ratings are just numbers on a certain scale, which will give you some sort of clarity about the concept itself, right? Now, if your TV show is talking all about stand-up comedy, let's just say, and you have someone saying, hey, I rate this 4 out of 5. Now, the advantage here is that you have a rating, as in you can understand on a scale of 0 to 5, maybe that 0 being the worst and 5 being the best, that this TV show is doing great. So you have a mathematical number there describing the data and giving you a hint at what the outcome might be. Now, if that TV show is rated at 1, what I would usually do is I would probably take a second guess to say, you know what, let's probably check this out sometime later. If it is 4, 4.5 out of 5, or if we go to IMDb scale at 0 to 10. So if there's a movie or a TV show that's rated somewhere above 7 or 8, I'll be very interested to watch that, because I know for a fact that a lot of people might have liked it. Right? So you're realizing what we are trying to do here. This is a key concept in statistics, and we have been using all of our lives, right? So it's not just this, whenever you're trying to assess and analyze maybe the current tax rate, you're trying to analyze what the level of inflation is, what the growth of the, what your country's GDP is and all of that. When you say statistics, all you're trying to do is have concrete proof of data, and through numbers, you can say, hey, this is the reason why this is happening. So you can provide a logical reasoning using numbers. Coming back to the TV show case, that's what you're going to do, right? You're going to look at ratings, you're going to talk to a lot of colleagues and friends, and you might even read reviews that other people have written, or you might watch videos where people are reacting to the movie, people are reacting to the TV show as well, right? Now, all of those things are data points. It's going to help you come to a decision saying, hey, do I want to watch this or do I not watch this? You realize that that logical decision at the end of the day is driven by metrics, numbers that you can track, assess, and verify. That, ladies and gentlemen, at the end of the day is everything that statistics is about. It is not us just going to perform some probability operations. It is not just us trying to understand how we can just solve a numerical or solve a problem mathematically. No. Of course, all of that is the process to eventually get to the result. The goal of statistics is to make sure you can have certain data points at hand, have trackable metrics for the same, and eventually work on your data to bring in some good insights, right? This is, we use this in multiple walks of our lives. We might do it every day on social media as well. It's just that we might not be familiar with the concept to a point where we would understand, hey, so this is what we're doing. But now that you have a certain idea about one example, can you think about 2 or 3 other examples where there are numbers which are guiding a logical decision? Well, let me actually give you one example as such. Just before we take a look at another example, this is exactly what I was saying, right? So you're making an assessment based on a number, maybe as a rating, maybe as the number of viewers, which eventually will help you decide a lot of things regarding the popularity of the show, the reviews, what people have to say. Is it something that is favoring to your favorite genre or not? Now, you might be a person who loves watching action movies. If this is a comedy TV show, there's a good chance even if it has good ratings, you might not watch it. But that is not a statistical decision. That is a logical decision you make. But if it is your favorite genre, you see the numbers help you make a decision. That is statistics. Right now, TV shows are one beautiful example to think about. Let me give you one more example, right? So, I am a huge fan of motorsports. I understand that here in India, a lot of people are cricket fans. We have a lot of football fans, hockey fans. There are a lot of sports that we play here in the country, right? So whenever you think about it, in my case at least, I am stuck to my screen with respect to motorsports. I absolutely love a sport such as Formula 1. And if you are a person who watches a sport such as Formula 1, or maybe the concept of even MotoGP, NASCAR, and all of these car racing, bike racing stuff, right? You have to realize one thing. As a person who's uninitiated into this domain, into the domain of watching motorsports, you might think that, hey, so if there is a race that is going on, it is just the driver who drives the fastest who will win the race. Yes, to one extent, you're correct. The driver who probably drives the quickest around the circuit multiple times, we call it laps, right? He or she will be awarded to be the best driver and, first place, second place, third place, all of that. But what you should be also analyzing is that, especially in the case of Formula 1, it is never just the driver who is responsible for winning the race. There is something called as strategy, and there is a pit crew that is sitting and assessing and analyzing every single move that you as a team make and what the opponent or what the competitors are doing as well, right? There's so many, fancy terms, overcutting, undercutting, and all of these. I am very sure if you watch the sport, you might get to know that. But my point here is that it's never a one-man race. It's always a team effort. So if the driver is driving the car, what is the team doing then? Again, the team are assessing many things. For example, at which part of the circuit is, maybe one driver can be super fast there. The other one might be very slow there. So if you analyze and assess a million details such as this, you will have a complete picture and you can have a prediction even before your race starts, saying, hey, if this driver can drive at this particular pace, our team can be fit in all of these places, right? So if you watched interviews before for a Formula 1 race, the team bosses or the drivers, when they're interviewed, they say, hey, realistically, we are trying to go for the second position. Realistically, we are trying to go for the third position. Not everyone on the grid will say, hey, we are going for the win, because of course it might not be possible in an extremely competitive sport. Right? The point here for you to understand is that it is not just one or two numbers that will guide the entire race, the win or the championship, but there will be teams sitting at the circuit. There will be a huge team sitting at a fully occupied factory who are all data analysts or just continuously churning the numbers to find out what are some of the possible outcomes that can come out of this race. Maybe the driver can win. Maybe the driver can come third. Maybe if there is a crash, then it can have a big dent in the world championship as well, right? All of these things are, when we speak about it, it just seems like logical decisions that you would take, yes or no, 1 or 0, but not really. Whenever you perform any calculations, do you understand that all you're trying to do is applying mathematics using certain data to provide meaning to the operation that you just did, and using that final result to have some decisions driven and maybe some key insights also driven? Don't you think that's happening? Yes, it is not just Formula 1. It is not just you watching a favorite TV show. Think about how all the companies around the world operate as well. Whenever they want to track efficiency, whenever they want to see what time it takes to deliver a product, whenever they want to, understand what is the best way that they can even try to solve a problem, there are numerous cases. And I personally want to say it's always a case wherein you can have a statistical concept there to help ease your understanding and load of working with a lot of data and give you meaningful results at the same time. That is really the beauty of statistics, right? So A coordinated effort of analysts, mathematicians, statisticians, and of course the racing drivers themselves in this example is basically what is leading to victories. So just like this, there are numerous cases that I am sure that you guys can think about which will have similar understanding on the whole as well, right? A very popular place where statistics is usually used is in the concept of predicting something that might happen in the future. Now, the technology we have today, especially in the world of data science, especially in the world of artificial intelligence, is that it is so conveniently implemented in our lives. We don't even find technology to be as amusing as probably it once was. I'll give you an example. Whenever you want to predict something, you will have to use mathematical numbers to go on to do that, right? Astronomy, astrology, all these concepts, in fact, also use a lot of mathematics and statistics there. If you want to predict what planet is going to move to which position, again, they do that, right? It's all the same. It's again statistics. If you want to predict probably what will happen in a race, or if you want to predict the outcome such as maybe tomorrow's weather, again, you're going to require a lot of data to be analyzed, assessed, and say, hey, if this is the amount of data that we can see and if this is the numerical result of it, maybe it will rain. Or if the cloud cover is not 100%, but it's 0%, it's going to be a bright blue sky, correct? You see how you can use numbers to your favor, be it in any logical situation which requires guidance or addition of meaning, which will help not just us understand a concept, but also get our machines to understand. Now, if I say, hey, how is the weather like to my computer? In its most fundamental level, it can only understand zeros and ones, but it has to churn through all of this data, figure something out, and eventually give you a working result. All of this should happen at the snap of your finger. Do this experiment right now. Go to Google or probably open up Siri if you guys use iPhones and just say, hey Siri or hey Google, what is the weather like tomorrow? By the time you even stop saying it, it would have given you an answer, right? So that is the magic. That is the power of statistics. So if we have been talking all this time about statistics and knowing that we have been a part of statistics, we've been using it in our daily lives every single day. So technically, what is statistics? Let me first talk to you about the definition of statistics. See, statistics is a very structured way of how you can collect data, how you can analyze this data and eventually use it to perform some predictions. Now, in all the cases, it doesn't have to be a situation where you're trying to predict something. Maybe you're just trying to describe what the data means in detail, right? Just like I gave you the race example, just like I gave you the TV show example. If a movie has an IMDb of 8 out of 10, you might think that, oh, this movie is going to remain popular for the next 3 years. Maybe that's not the case. Maybe you're not trying to perform a prediction. Maybe you're just trying to say, hey, why are people liking it so much at this moment of time? Can't you answer that question? Well, yes, right? So be it predictions or be it describing your data numerically, if you want to find a structured way to go about doing this, the method, the concept, the domain of statistics is what you guys should be looking after, right? So we understand where we've used it, we understand what statistics is, but with the same moment of time, you guys will also be curious to understand what are these various types of data that we can go on to come across when working with statistics, right? Of course, data consists of raw information, right? Now, when you say information, it must be useful. But when I say data, it doesn't have to be useful, right? It can consist of things which may or may not help me. Now, in this particular case, data happens to be of multiple types. And when you're a person who's looking forward to applying the concepts of statistics there, you must understand that there are different statistical concepts involved in handling different types of data, right? But to get to that point, you need to understand, okay, so what are these various types of data that we have? On your screen, you'll find two commonly used types of data that we have. One is categorical data. The other one is numerical data. Now, from the example that you see on your screen, can you quickly take a second to actually guess what categorical data is and guess what numerical data is? Because let me tell you, it is very straightforward. Categorical data, when you say categorize something, you're trying to align it in a textual format, and categorical data is mostly textual data as well, right? In fact, in categorical data, there are three types of data: ordered data, nominal data, and binary data. When I say ordered data, think about ranking: first rank, second rank, third rank. Think about the priority of maybe a job. Maybe you guys are in your college or in your job right now, in your career right now. When someone says, hey, this is priority number 1, this is priority number 2, this is priority number 3, it will feel like, yes, even though it's a numerical metric that is attached to it, with respect to how categorical data itself is split out, you have an order to it, right? 1, 2, 3, first rank, second rank, third rank, priority 1, priority 2, priority 3. Be it the driver winner 1, runner up 1, third place. All of these, right? You have numbers and you have an ordered way of even conveying textual data. That is ordered data. When we say nominal data, it's basically us talking about anything which is unordered, right? Let me give you a small example. If I try to measure height, right? Now, I'm sure everyone will have a small mark on their wall or something like that, wherein they would have tracked their height over the years. You will see that height it's not just increasing in one way. There might not be any order to it, right? If you're a person who works out very heavily, you'll realize that your body will actually expand and contract a lot. If you're measuring it on a daily basis, you'll realize that one day you're slightly half an inch taller. The next, you might have, maybe not for the day, but maybe for a week, you would have worked out with a lot of weights. That will slightly compress your height as well, right? So all of these things will vary, and there might not be any set order to say, hey, once you start growing, your height will go up and up and up until your last day here. Not really, right? So that can be considered as unordered data. There is one more type of data with respect to categorical type of data, which is binary data. Binary, ladies and gentlemen, is very simple. It's you splitting your data into two: yes or no, 0 or 1, true or false. Think about it. In how many situations in all of our lives we've come across this type of data, right? When someone asks you a question and says, hey, don't you think this is correct? There will be two answers you can give. Yes, it is correct. No, it is incorrect. So when someone asks you, hey, is this valid? Again, two answers. Yes, it is valid. No, it is invalid. Right? So yes, no, whenever you have two choices to make, and whenever even you have a textual context or a textual reason through which your answers can only be in two forms, that is basically binary data, right? Even in the real world, that's how true binary works as well. So I hope we're clear with categorical data. Now it becomes very difficult to measure categorical data at the end of the day because it is textual. Not all the examples you can discuss can be measured, right? But what we can talk about with respect to numerical data is actually something that you can measure, something you can assess with respect to mathematics and statistics. So if that is the case, what are some of these types of numerical data that we have? There are two types of numerical data which you guys might already know about. One, first of all, let's talk about continuous data. The second one, because this is the data we usually come in contact with every single day, right? So when you say continuous data, there will be a constant graph which you can track and plot to assess. For example, if you want to track the age of a person, they start at 0, basically their day 1 of birth. Next, first year, second year, third year, fourth year, fifth. It will never go down. You never go from being age 5 to being age 4, right? It's only continuous. It is going only in one direction. Even the height of the person to a certain extent is considered as continuous, because you can have a continuous curve to plot it. You can have a very beautiful sine wave kind of a curve to actually plot something like that. But if you are talking about discrete data will not come with any sort of order that is built into it, or it is not something such as it's continuously moving, right? Think about the days in the calendar. Now you might say, hey, every month has 30 or 31 days, so there is a pattern in here. So why are we considering it as discrete instead of continuous? Very good question. Now, what happens is that every month we start at date 1 and we probably go to 30th and we probably go to 31st. What happens after that? Aren't we resetting it back to 1 and starting all over again every single month? So that kind of non-continuous ability until day 1 to 30 or 31, it is continuously growing. But at 31, there is a cut and we're eventually trying to circle back to the same thing and do it again, right? This is a very good example for discrete data. Now, I've heard one more fantastic example, which is basically your mobile numbers, right? Whenever you have your mobile number, there is probably an order to it, which whoever is your provider is trying to maintain or something like that. But for you, in your context, in your reasoning, it's just a number that is associated with an identity or something, right? There's no continuous nature to it from your perspective. If your number starts something like 8884 or something like that, again, can you plot a curve for each of those numbers and make sense? Not really, right? That is discrete data, ladies and gentlemen. Now that we have a good amount of understanding trying to say, hey, so we know what statistics is. We've taken a good look at its examples. We know what are some of these various types of data that might occur that we'll have to handle on the lines of categorical and numerical data. The next thing that you're going to be curious about is to understand this particular concept saying, okay, so now I know the types of data. What should I do, or how do I even collect this data, and how do I make use of it in the concept of statistics, right? That is exactly what we are going to take a look at now. Ladies and gentlemen, whenever we're talking about collection of data, let's just take a step back and analyze how we have done it in real life, right? So if someone says, hey, there are 10 oranges in front of you, just pick out 4 of the best oranges out there. What will you do? Out of the 10, you'll find probably the 4 brightest looking or the most juiciest looking oranges, and you'll pick them up or something. So what is it that you're doing? Overall, there are 10 oranges. You just picked up 4 out of it. So you're taking a subset. You're taking one small, let's just call it as a concept called sample from it while you're leaving the rest there, right? Exactly the concept. If you consider the entire 10 oranges, it is called as a population, because that is everything that exists in our country, in our focus, in our problem statement there. And once you say, hey, I only want to pick up the 4 oranges out there, you're trying to pick up certain samples there. And when you pick up 4 out of 10, these 4 elements, oranges, or in our case on your screen, as you can see, flowers and plants, they can be considered as a sample set. On the left, what you see is something called population, as in this consists of all the data that is out there. On the right, you're just picking up a part of the data, which eventually is part of the population. If we're talking about human beings on Earth, when you say human beings, all of us, we're all on the same playing field, we're all on the same league here. But when you say, hey, maybe I need to hire 10 Australians, maybe I need to hire 10 Indians, I need to hire 10 Americans. Now what are you doing? You're taking that entire world's population and you're picking a sample set from that, right? So this concept of just picking 1 or 2 out of a large set of entities is nothing but sampling. Now you might ask a question saying, okay, so if you're collecting data, why not collect it for everyone? Why should you even go on to sample something? Why should you break it down into just 4 people? Maybe that 5th person will have some idea or something which I can use. And if I just pick up 4, it might hurt me more than helping me. Very good point, but let me tell you one thing about sampling. When you break things down into simple chunks, not just for you to understand, but statistically even for your machine to understand, you are getting an even better look at assessing what your data is doing, what can it tell you in terms of each individual entity's contribution to a population or to the solution of your problem. And at the same time, it can also give you guidance about maybe using the data for pattern matching, or maybe using the data to drive certain decisions, which would have been very difficult if you just took all the oranges out there. Now, instead of picking up 4 oranges, if you had 40,000 oranges and you just said, hey, now sit and assess all the 40,000 oranges, maybe it all looks the same. Maybe it is very time consuming for you, and it might almost seem meaningless to sit and run through 40,000 oranges when you can probably just do it for 40 and say, hey, I did it for 40 and it seems to be the same for 40,000. Which is the more efficient process here? I am sure you understood the concept of sampling by now, right? So, is it only sampling that you can use? The answer to it is actually no. But since we're still talking about sampling, how do you sample it? If I say, hey, pick up 10 oranges from a crate of 100, if you just put in your hand randomly and pick up these oranges, there is one way that you're doing. You're randomly picking it up, right? Now, here's one concept which can get slightly confusing for beginners who are into statistics. When you randomly actually put your hand into the basket and pick it up, maybe there is no thought in your head and you just randomly, maybe you can even be blindfolded and you can pick it up. That is random. When you ask your computer to create something random, it is never random, let me tell you this. Even though there are numerous functions, numerous things which will help you scramble things and create randomness out of it, to create those random things, your computer is using an algorithm. It is using some set structured process to actually move your data in a particular way. So there is an algorithm that is powering that. Right now, of course, that's all in the depths of advanced statistics. We don't have to touch all of that right now, but that is something you should always keep in your mind as well. So randomness, we understood. You just close your eyes, you pick up 4, you are done. But what is this other thing we're seeing on the screen that says clustering? Let me give you an example. Now I'll say, hey, here are 100 oranges. Take a look at it, out of which some of them are not fully ripe, as in some of them will not be fully sweet to taste maybe. So find the ones which are maybe ripe and just keep it aside from all the ones which are still raw or unripe or something, right? So now you're trying to group things, ripe oranges, unripe oranges, something like that, right? So you're dividing, you're clustering in a way where you're just picking up certain things and you know what it is that you're looking for and you have a way to assess why you did that. That is basically clustering, right? So you can pick up multiple samples out of a population either randomly, or you can have a decision, or you can have a pattern that you can hunt to pick up the data as well. So this is one very, very important concept of how you can go on to collect the data for statistics. So with this, you guys should now be very clear about understanding and assessing, hey, so these are some of the reasons of how we can go on to collect the data and work with it, right? In fact, before we take a look at the types of statistical analysis, can you think of more examples regarding random sampling? Can you think of more examples with respect to clustering? Just give it a thought, make a note out of what are all the various things that can come into your head. I just gave you one orange example, but there has been many places where you would have picked something randomly, or there are many places where you have organized a data point or something like that because you have a valid reasoning to go on to do that. If the concept of randomness and if the concept of clustering is not clear for you on a simple foundational level, going ahead as a person who's very interested in statistics, things can get really, really difficult because you'll be handling a large amount of data. To do it for 10 oranges, piece of cake. To do it for 100 oranges, somewhat difficult, but you can do it. Now, if I say, hey, I have an entire farm and I have 1 million oranges for you to sit and assess and analyze like this, what would you do? Again, you would take the entire population, you would sample some of it you will pick randomly to sample, some of them you will actually find out saying, hey, this is ripe, this is big, this is small, this is not yet matured fruit yet, something like that, right? So you have a way of assessing and analyzing, and you have done it in various situations. I want you guys to think about it, because having the understanding of how you would have approached something without even thinking about it previously, wherein a concept of statistics was involved, is something that's going to help you solve future problems as well. Now we understand what is data, what are the types of data, how we go on to even pick up data to perform some sort of statistical analysis. So what are the various types of statistical analysis that you can go on to perform, or what are some of these various types of statistical analysis that you can use to solve a variety of problems? Well, there are two very, very popular ways of going to perform whenever you're going to perform statistical analysis, which is nothing but qualitative analysis and quantitative analysis. Now, for the people who are familiar with the term qualitative, for the people who are familiar with the term quantitative, you can find out what it means just by the words itself. Quantitative talks something about quantity. Qualitative talk something about quality, right? Let's talk about the example that you see on your screen right now. With respect to quantitative, let's close quantitative first so you will understand qualitative better. Now, if I say, hey, how many pens or pencils or whatever it is that you can see on your screen right now, what would be your answer, right? So there are 16 pens and pencils here. That's a quantity. Now, if I say, hey, why don't you pick up 3 pencils out of 16 pencils? right? And analyze maybe if those pencils are right, correct or wrong or something, or if they have any manufacturing defects. All of these situations, you can have hundreds of situations, but you're performing analysis on a numerical metric directly. That is quantitative analysis, where quantity, where you're driven by a number as an input itself. But what about qualitative analysis? Now, qualitative analysis also you can do with respect to statistics. Let me give you an example. Let's just say there are 4 colors of different ink pens that you see on your screen right now. And maybe 2 of these are extremely expensive and they write beautifully. We know that pens that people use to write to put in a signature can sometimes get really expensive, right? It's made of silver, it's made of gold, and all of these different reasons. So maybe some of these pens write really well. So when you say it writes really well, what are we doing? What are we assessing and making a conclusion on? We are saying that, hey, this pen maybe is very smooth to write. Maybe the way it puts the ink down on the paper is very clean and you would like it. Correct? So you're assessing it based on quality. Now, quality, you might say, okay, so if we understand quality in terms of statistics, how can we put it in numbers? How did you put a TV show in terms of numbers? You had a rating to do it, where you had a range. In the range, you realize 0, it's very bad, 5 or 10 being amazing. Similarly, for qualitative analysis, even that example of TV shows is qualitative analysis. Here, what we are trying to do is we're trying to assess the same thing. If your pen is like very scratchy, it is tearing your pages, it is not depositing enough ink on your screen, you can say that, hey, the quality of this pen is bad. You've done this and you can say, if someone asks you, okay, so how bad is the quality? You'll say, on a scale of 1 to 5, I find it to be a 1. Right? Now you have a metric to track quality, and with respect to quantitative, you have a metric directly to analyze. So either ways, either situations, logically speaking, you can convert and bring all these concepts right down to the fundamental level of mathematics and statistics. And don't you think, with the details that you would have had at your hand at this moment of time, that if someone asks you which quality of pen should they buy, with your analysis here, don't you think you can give them a numerical answer? That is one very important thing you have to understand about the types of statistics that we have out there. Right? Now, we checked out with respect to qualitative and quantitative analysis, there are 2 more types. There are further divisions in the chart of types of statistical analysis, which is nothing but inferential statistics and nothing but descriptive statistics. Now, inferential statistics and descriptive statistics. As you know, the course is called Descriptive Statistics. So what are we trying to understand here? To understand descriptive statistics, you need to have a clear understanding of what inferential statistics is. Now, when you say inference, you're trying to infer something. What are you trying to do? You're trying to assess something, you're trying to assume something, or you're trying to infer something. Now, a simple example in inference is that, hey, right now in Bengaluru, that's where I'm from, it's actually very cloudy. It is super overcast right now. It's very dark in the afternoon, but I can infer something saying, if this is the case for the next 30 minutes, maybe it will rain. Or I can say, sure that I see the darkest clouds in the sky right now, it will rain. So you're making an inference even before the situation occurs, on the same lines of prediction, correct? That a concept around that is inferential statistics. Don't worry, we're going to take a look at it in detail. And then coming to descriptive statistics. Descriptive statistics is when you're trying to describe something on the fundamental level. What are you trying to describe? With respect to how one can go on to either describe and digress a problem, or how you can go on to explain a solution, or how you're working with your data. If you can describe that, either be it in a numerical way or in a logical way, that is descriptive statistics. So let's have some more clarity on these concepts. Let's try to understand, how we can go on to work with inferential statistics, what is descriptive statistics, and how we can work with that as well. So, to perform inferential statistics, you must understand one thing. Whenever you're trying to infer something, you will usually prefer, again, a sample space or a sample set from an entire population. In real world, even in small examples, while you guys are learning, you would have given 10 elements and you would have asked to analyze 2. What is that again? Population and sample set, right? So with respect to performing inferential statistics, I am not saying, hey, I can count 10 clouds in the sky. That is impossible. I can generalize and say there are a lot of clouds. And you might say, is this okay to say there is a lot of clouds when we are especially trying to infer something? It is okay, even though it's not a direct metric, having a generalization will still get you to your answer, right? Give it a thought. That exactly is inferential statistics. So let me give you a small example to help you understand. Now, if I say, hey, there is a sale going on. There are 18 sedans for sale, 4 SUVs for sale, super utility vehicles, and there are 3 convertible cars that are for sale. Now, if I ask you a question saying, in all of these sedans, SUVs, and convertible cars that are for sale right now, which is the major type of car that is being sold? Can you not answer that? Can't you just look at the data there and say, hey, so there are 4 SUVs, 3 convertibles, but 18 sedans being sold. So the number of sedans are the ones which are being sold the highest, right? They are the highest number of cars being sold basically. So you can come to a numerical decision for a logical problem based on categorical data having numerical tracking, right? Now, if you slowly rewind and listen to me one more time saying that, it will make complete sense to you all, but I'm sure it's a very simple example you can understand, right? Lot of cars, which type of car? You have a metric to answer, it's a direct pick and place. That when you're inferring something, when you're asking a question, which type of car sold the most? You're saying it's sedans. And when someone asks you, okay, how did you say that? Well, there's all the data in front of you to help you drive towards a decision. Every single step that we are just logically speaking out, or the logically I'm explaining to you, there are numbers involved everywhere. And eventually these numbers, exactly as I've been telling, is what is driving the eventual solution. Don't you think? That is inferential statistics. Now coming to descriptive statistics. Descriptive statistics is exactly what all of us are after in this particular course. But one important thing for you to, if you just dive right into the concept of descriptive statistics, it becomes very difficult to assess and analyze later on. Because if you do not know what are the types of data, if you do not know that you have some real world connections to statistics that you have used, when you're working on real world data, it becomes super difficult for you to assess. Now, descriptive statistics is basically describing the data that we have at hand. Let us take this exact same example we discussed there. You have 18 sedans for sale, 4 SUVs for sale, and 3 convertible cars. Now, if I ask you a very specific question where your answer describes the entity in discussion, that is descriptive statistics, right? So if I say, hey, how many sedans that are being sold out of 18 are blue in color? So you will maybe say, hey, there are 4 sedans that are blue in color that are being sold. You're describing not just a sedan, but the color of the sedan. And eventually you will say, okay, out of these 4 blue colored sedans, out of the 18 sedans, there are 4 blue and there are 5 sports models as well. Sportier versions, which maybe they go faster, or, they accelerate quicker, they have better performance, something like that. So can you or can you not describe the data that you have at hand, be it using numbers or be it using logic in this situation as well? If it's a simple question of how many sedans, we answer it by making an inference. If I say, okay, so how many sedans of blue color, how many sedans which have 18-inch rims, something very specific, very detailed, which will have your answer to describe the entity in discussion. Ladies and gentlemen, that is descriptive statistics. Now we just took the entire complex world of descriptive statistics and understood it using a very simple example. Is descriptive statistics really this simple, or is it really this straightforward every single time? The answer is yes. The concept of how you apply statistics, the concept of how you describe something is going to remain the same. What becomes complex is the fact that you will have a lot of data that you have to use to get to this point. So it's never really as easy as looking at a crate, picking up 10 oranges from 100. What if you have 100 million oranges? What if you have the entire world's oranges in your farm right now, right? So when you think about situations like that, sometimes descriptive statistics will work in your favor, but sometimes to go on to perform the process itself, it can get cumbersome. So how do we solve this problem? How do we find ways through which we can measure so many things? Maybe you want to measure something in terms of accuracy. Maybe you want to have a metric that will just describe the data which if you just look at your screen right now, 18 sedans, 4 SUVs, 3 convertible cars, you can probably find out the total number of cars that are sold. You can find the colors of the cars, types of cars, and all of that, right? Now, if I ask you a question, what is the average number of cars that was sold? Do you have data ready on your screen to tell you that? No, you have to perform some calculations based on the data at hand to give you that answer. What is the average number of cars that were sold? What is the minimum number of cars that were sold? What is the maximum number of cars that were sold? You're getting this right. You still have to describe the aspect of using the concept of statistics, but in this particular case wherein you will have to perform some operation to give you the description that you require. That is where we have a lot of measures that come into the picture. Measures of central tendency, measures of accuracy, measures of variability. All of these things are at the heart of statistics to a point where you will completely assess and analyze and come to your answer through certain operations powered by your data. And that is exactly what we are going to check out from this section till the end of this particular course. We're going to start this out by understanding something, a concept called as measures of central tendency. Now, if you have come from technical learning platform, or if you've come from maybe a mathematical education from your school or college or something, I can promise you that you've used central tendency, you have learned about it, and you never knew that it is called central tendency as such. Or you would have used this in real life as well, right? So if I say, hey, there are 10 apples in front of you, 3 of them are bad, 4 of them are very good, and maybe 2-3 of them can never be sold, something like that. If I say, what is the average number of apples that can be sold? You can just say 7 out of 10, 6 out of 10. So you have an average number to give me, right? So those are some numbers which are describing the data which you cannot find out looking at it through the naked eye directly, right? So certain numbers, mathematical operations describing the data. I am sure now that you looked at your screen, you can understand that there are 3 measures that we use to describe the data with respect to central tendency, which is the mean, which is the median, and which is the mode, right? Now that you know it, I'm sure you can guess what all of them mean. But for the people who have never worked on statistics, mean basically represents an average value in the entire data set. Now, what about median if that's the case? Median talks about a middle value. Now, if I just give you 10 different cars, maybe in the order of 1 car being new, slightly used, very much used for 10 lakh kilometers, something like that. There is an order to it, right? You're ordering it based on the number of kilometers that the car has been driven for. In that particular case, if I say find the one in the middle spot, I don't want a car which is brand new. I don't want a car which has been used to a very good extent. I want something in the middle, right? I want something around the approximate, around the average. People usually use these terms in real world in conversation. Now, if you do not pay attention to this word which says ordered data set, because if I just give you these 10 cars in random order and say pick the middle one, do you still think the middle one is going to give you a clarity about it being the midpoint there? No. You might have the car which is brand new to be sitting in the middle spot just because your data is not ordered. So whenever you're trying to find and work on the median of it, you are going to require some ordering. Now you might say, if I require that for median, do I require it for mean? Absolutely not. Why? Because when you're performing an average operation, regardless of the order you put all the elements, add it up and divide it by the total, it will still remain the same. 2 plus 3 by 2 is still same as 3 plus 2 by 2. Think about it, right? So mean, you just require the data. You don't require any ordering. Median, you require the ordered data set. So what about mode then? Mode basically is giving you some sort of clarity about how many times a certain number is occurring, right? So if there are 10 elements, if I just give you numbers from 1 to 10, if it is in an order, fine, you can find the median. If it is not in an order also, you can find the mean. Now, if I say find the mode will be basically an entity, an element in discussion which is repeated the maximum number of times. right? So I hope we are clear with this. So let's actually dive right into small examples to take a look at mean, take a look at median, and take a look at mode. Alright guys, so to talk to you about the measures of central tendency, the first one on our list is mean. Now I already told you that mean is a very simple calculation of an average, right? Now look at all the data elements that are present on your screen. We have 100, 150, 200, 380, 450. So you see that there's no order that you see on your screen, right? There's no ascending order, there's no descending order. Can we still find the mean? Of course we can, because regardless of you adding it in any order, it's still going to give you the same result. So how do we find the mean? Take all the data elements and add each and every one of the entities that are present there. Once you want to add all of them, divide them by the total number of elements. Now in this particular case, you'll see that there are 10 elements. So we're going to add each of those values divided by 10, and this is the average value, 238. Now it's a very simple thing. If you guys have watched cricket or if you watched football or something, they have told you the average runs scored by the team. You know, what is the batting average, bowling average, all of that, right? So how do they even find that? They just take a lot of data from the game in any order and eventually give you this thing, right? It's very simple, yet it is one of the most powerful concepts that governs the world of descriptive statistics. So if I just look at the data, don't look at the mean part, just look at the data. If you just look at it, if I ask you what is the average, without any calculation, can you give me the answer? No, you'll have to perform some calculations either in your head or on the paper, right? That is where these measures that you directly cannot see, but yet once you start finding them, they will give you so much more insight about the data. They'll help you describe the data better, right? That is descriptive statistic. Coming to the median now. Median, I told you really have to have ordered elements, right? Without an order, finding a median is meaningless, because if your values are jumbled, you're not trying to find any structure in that information. So the first one that you see here is our original list of elements. It is as we saw in the mean case. Now what we've done is I've rearranged the data in the ascending order for you guys. Now you'll see that the numbers are continuously increasing from left to right. So if that is the case, if I say, hey, find me the median of the data. Now here is one case where people might get confused. Okay, so if I'm just looking at 10 elements, which is the middle element, there is no middle element in 10, right? There never can be. If you have even numbers, the middle one is, you can never have one. It will be either 2 or it's none, right? Similarly, when someone asks you to find median for a data which has even number of elements, just find the middle 2 elements, take the average of that. Here it will work because the data is arranged. Here it will also work because you're just finding what exists between these 2 points. Now if I do 150 plus 100 by 2, it is nothing but 250 by 2, which is 125. So if there were a median in this particular case, it would have been 125. This is a complex case. However, there can be a simple case where you have odd number of elements. If you have odd number of elements, you can find the middle one easily, right? Look at this. If there are 9 elements, there are 4 on the left, 1 in the middle, 4 on the right. So the median is very straightforward. Just pick up the number 100 and eventually put it out there. You don't have to perform averages. You don't have to find the mean of the middle elements to find the median. Right? I hope this concept is clear. Now, we're done with mean, we're done with median. What about mode? For mode, it is very different from all the other types of data, because here you really do not require any sort of order. You do not require any sort of meaningful metric to actually find it. All you have to do is look at the frequency of occurrence. Here, look at this. If I say mode is 150, it means that 150 is the most occurring element out there, right? Look at this, 150, 100, 200, 150. This 150 is the one which has been repeated most of the times. As simple and straightforward as that. This eventually has to be the mode. Now, where would you use mode, right? If I tell you, hey, there are 5 oranges, pick up 4 oranges which are ripe. The logical understanding is they are ripe, but you're trying to pick the most number of one. Even if I don't tell you pick up 5 oranges, if I tell you there's probably unripe mangoes or something which is green in color, there are ripe mangoes which are yellow in color. If I just say pick up all the ripe mangoes, you'll find the ones which are yellow color, find the maximum number of yellow colored mangoes and pick it up. Simple, right? You have used mode everywhere. You've used mean everywhere. You've used median everywhere. Just the fact that you might not know that it has this kind of a statistical value is what the bridge we are trying to gap here, right? The other thing that you have to understand is that it is not just mean, median, and mode which governs the world of descriptive statistics. It is a lot more from that. In fact, we have something called as measures of variability. What do you mean by variability? Something that varies. Can you track something that varies? The first thought that might have come to your head right now is, no, we cannot track something that varies. Well, when you say something is varying, you have a range of data to tell you that it is in between this range that it is varying, right? Now think about the concept of it raining tomorrow. If I say there's a 30% probability or there's a 30% chance that it might rain tomorrow, that 30% is basically a number between 0 and 100%, correct? So I have a range. So the data points there can vary enough to give you a metric output, right? Now, when we have to showcase a range of data, when we have to have a measure which will govern part of the data in the range, well, that is when we go on to take a look at variability. In variability, there are three things you have to learn with respect to descriptive statistics, which is range, variance, and standard deviation. Let's take a look at range first. When someone says, find me the range of the data that is present there, or find me the range of the car that you are trying to take a look at, what is the range that you are trying to look at when you are purchasing something? You would have heard this term at the shopkeepers a lot, right? Maybe when you're in a market, whenever you're buying a new car or a bike, they say, what's your range? What range are you looking at? So that term gets thrown around like confetti, but at the end of the day, range, when you have to calculate it, is a very simple calculation between the highest value subtracted it with the lowest value. So the highest value minus the lowest value will give you the range. In this particular example that we have, regardless of what value will repeat how many times, all of that we don't care. All we try to look at is find the maximum value, find the minimum value. Max minus minimum, that is your range. So a range will tell you the difference of how your data will actually vary with respect to data points. Now, if your data can talk about its variability just with the fact of finding minimum and maximum, can we dive into the depth and try to understand how your data is spread across in a range? That is where a concept called as variance, that is where a concept called as standard deviation comes into the picture. I am sure if you have learnt mathematics in school or college, you would have come across these terms and you would have solved examples on these as well, right? So what is variance? Variance is basically a concept which will talk about how your data is spread compared to what. When you say spread, you can, if I just say, hey, spread these oranges around, you can throw it in your farm. You can keep one orange in India, one orange in America. You can, there's no range. If there's no bound, you can never say that the spread is valid, right? So to keep the spread valid, we have a range of data, and eventually what are we comparing the spread to? In the case of variance, we're basically comparing that to the mean of the data point. Now we calculated the mean for this entire particular data to be 238.6 previously. So how do we find the variance with respect to each data point to the mean? Well, it's nothing but a very simple operation of squaring the differences between mean and each of the value. So you have mean value, you have one mean value, you have multiple values. All you have to do is find the difference between the mean and each of the value, square it up, find the average of the entire thing, and that will give you the value of variance. In this particular case, you can see that the variance value is somewhere around 67,321. How did we get to that? Let me quickly repeat. Find the mean of the entire data set first, find the difference between mean and each and every one of those data sets, and eventually have the average, square that entire number. That is what will give you your variance. If that is how you find variance, then how do you change? How do you understand with respect to your mean value? How do you figure out this is how my data is spread? Data spread can be figured out by something called as standard deviation. How does your data deviate with respect to its each point with respect to the mean? That is standard deviation at simplest form. Now it's very simple and straightforward, guys. If you have found variance, Just take a square root of that variance value, and eventually if you take the square root of 67,321.8, it is giving us somewhere around 259.4. So we're trying to say that, hey, this is how much the spread of the data is, and this is the range through which the data is spread whenever you've compared it to the particular mean. Right? So guys, with this we are clear with mean, we are clear with a median, we are clear with mode. That was central tendency. Now with respect to measure of variability, we understood how we can calculate range, we understood how we can work with variance, and once we understood variance, take a square root of it, it's standard deviation. But why the square root, or why taking the square root will give you what, is exactly what we actually figured out. Correct? Fantastic. Now after measures of variability, you will also have to take a look at understanding, hey, with respect to data, can we measure relationships, right? Now, think strictly in the term of numbers here, guys, because whenever you're trying to understand relationships that exist in between two data points, you can have two concepts here, right? Anytime you have an interdependency of values, it can be on the range of covariance and it can be on the range of correlation. So what is covariance? What is correlation? The concept of covariance is very simple. Here, what we're trying to do is, instead of comparing two direct values, we're just comparing and denoting the variance that exists between 2 points. And when I say two, in real world, it is never two. You can have any number of data points and you can find the covariance there. Right? Now, there is something called as positive covariance and there's something called as negative covariance. Positive covariance is when, there are all the elements that are in comparison is moving across the same vector, same plane, same direction. Okay, so can you give an example? If your engine rotates in the first gear, your engine rotation, and there's a very good chance the way your car moves is still going to be the same direction, right? So there's a positive covariance there. Now, if you use a lot of gearing, of course, there's a lot of gears used in your car, and it is not just that it will only go in the forward direction. You can put it to a reverse gear, even though your engine is running at the same speed, even though your engine is running in the same direction, those gears will make it run in an opposite fashion, right? So if your engine is still rotating forward, but your car is moving backwards, that is because there is a negative covariance that is put into there, right? It is negative if either of your data points move in a different direction. Numerically, if you have something that's going on the positive side and eventually the result of those positive numbers are decreasing negative numbers or something, that is nothing but covariance. You should be asking a question right now. We understood positive covariance, we understood negative covariance. What about zero? Well, if your data elements are zero, it means you cannot have anything to compare to that particular point in the example that we just spoke about, right? If all of your data elements, if you have 10 zeros, if I say find the covariance of all of these, nothing is varying for you to find a distance. If one point is zero, everything that has to do something with zero is going to remain zero. 0 multiplied with 0 is 0, 0 plus 0 is 0. So covariance will not exist in that particular case, right? So I hope we are clear with covariance. Now that we're done with covariance, the next thing that we're going to have to take a look at is correlation. How can we denote some relationship that exists, not just in terms of how it varies, but what it is in its most basic form is nothing but correlation. I'll give you a very simple example to explain correlation. Now, when I say, hey, I have been eating a lot of sugar, I've been eating a lot of unhealthy food, a lot of cheese, and I'm not doing any sort of exercise, there is a good chance that there can be an onset of diabetes. As per age, if your age keeps going up, there is a certain chance you can still get diabetes, correct? So there is a correlation between age. Age is related to diabetes. Then if I say there is blood pressure also has an impact. If you are a person who has a normal blood pressure, maybe it has nothing to do with diabetes. But if you're a person who has high blood pressure, based on all the medical reports out there, your doctor might say, hey, your blood pressure is high and this is what is causing diabetes for you. You just heard the statement. You have high blood pressure. This is what is causing your diabetes. So you found out a cause through a point by having a relationship interlinking these two concepts, right? That is basically this. So with respect to bringing all of it in the terms of numbers, we will have a range of values through which we are worked with. So if I say that, hey, there is a correlation of 0.9 in between age and in between diabetes, it means that your age is very closely linked on how much impact it can have on diabetes. If I say your age has 0.1 correlation with respect to diabetes, it means that, hey, age has very tiny amount of factor or tiny amount of say in how you would get diabetes, right? Very simple to understand. Now you must be asking one more question. Okay, so we just spoke about 0 to positive numbers. What about negative correlation? Negative correlation also exists. You've been using it all your life. You just go to the nearest petrol bunk, you just get a full tank of petrol. Now, as in when your distance you travel on your bike or your car increases, the amount of fuel decreases. So what is the relationship? There's an inverse relationship. More the distance you go, more the fuel, of course, it takes. But if you're talking about quantity of fuel versus distance covered, the more distance you cover, the quantity of fuel will be coming down in your fuel tanks, right? Very simple case. This is how mileage is also calculated when you think about it. Where every time you try to assess and analyze a real world situation, next time do this. Try to assess in a way of how you can statistically figure something out, because once you can go on to do that, you will figure out a lot about your data, which you can say initially this would have never been possible. Now that we're done with the measure of relationships, the next thing that we're going to take a look at is the measure of skewness. Now, when I say something is skewed, what do I mean? Skewness is basically talking about how unsymmetric a data point can get with respect to some position, right? Now, let me explain with the example that you see on your screen right now. There's something called as normal distribution. So once you plot a curve for a normal distribution, your data will be distributed equally to the left of the mean and to the right of the mean, as you can see. This is symmetrical data. In symmetrical data, your mean, your median, and your mode is going to remain the exact same thing. Because your mean is the average of data, your median is the middle point, and your mode talks about the maximum occurrence. In this particular graph, you will see that all of those points will be right here in the middle. When that is the case, it is nothing but no data which is not skewed. Of course, in the real world, this never is the case. There is going to be either some change in the positive or the negative direction. So to understand that, what we're trying to assess here is what level of asymmetry is basically present in the data around us. So there is negative skewness and there is positive skewness. Remember, this is a very important point in discussion, because with respect to negative, with respect to negatively skewed data, your mean will always be less than the median, and your median will always be less than the mode, right? So quickly going back, it should show you that the points to the right of the data will have higher values than the points to the left of your data. If that is the case, it is nothing but negatively skewed data. If we have positively skewed data, it is different. Here, the least value is going to be your mode, your maximum value is going to be the mean. Because why? If it is positively skewed, there is more data to the right side of your mean, correct? Look at that. In this particular case, if your mode is less than median, which is less than the mean, look at the shape of the curve here. You will understand where the mode is, where the median of the data lies. This is the midpoint of the data, mind you. Again, in the midpoint of the data, if you take a look at the curve, everything left of the curve has more data to assess and analyze, while to the right of the median, there isn't, right? So guys, this is skewness. When your mean is less than your median, which is less than your mode, it is negatively skewed data. When you have your mode less than your median, less than your mean, that is positively skewed data. Now, I know it can be very difficult for you guys to assess and analyze this. That is the reason I have this diagram. Take a note of it, and importantly, take a look at understanding why it is the case. I just explained negatively skewed and positively skewed, and I told you why it happens, right? Take a note of that, and especially this part, right? Mean less than median less than mode, or mode less than median less than mean. This is super important, guys. So make sure you're taking a look at all of that. Now, after you've understood the measure of skewness, the next thing you're going to be very curious to take a look at understanding is something called as kurtosis or kurtosis. Now, there's many ways people usually spell it. I pronounce it as kurtosis. Now, with respect to kurtosis, this is a very important concept which finds itself in the heart of descriptive statistics to a point where it is used in finances, it is used used in market analysis. I just want to say it is used in most or all of these domains. So what is kurtosis? We saw what a symmetric distribution looks like. We saw what a normal distribution curve looks like. What we did not analyze is how big the curve is, how sharp its edges are, and what does it mean if you have a fatter curve? What does it mean if you have a slightly thinner curve? To assess that, we have kurtosis here, guys. So you might say, hey, there also we are trying to find more data present on the left for positive skewed, more data on the right for negative skewed. So what is the difference that lies in between skewness and kurtosis? Let me tell you this. Skewness will talk to you about the degree of the slope that is present in terms of frequency distribution, as in how is your data distributed on the slope of the angle, right? You can find that out. But kurtosis talks about the degree of thickness of the tails, because you might be a person asking a question right now. Okay, so if the tail is thicker or if the tail is thinner, big deal. What does it mean? It means a lot of things in the world of statistics, as I'm going to tell you. In fact, to understand that, we'll just take three different cases. In fact, these are the three types of kurtosis. One is leptokurtic, the other one is mesokurtic, and the other one is platykurtic. What are these? First of all, this is the black line you see in the middle is called as mesokurtic, and this looks relatively normal, right? If you ever take a look at a normal distribution, it's going to be something like this. It is slightly bulged at the top and it just flows up and flows down, correct? But take a look at leptokurtic. With respect to leptokurtic, it is a very steep climb, and as soon as the steep climb is done, since it's normal distribution, there's a very steep descent, and you will see that it's very different. On the left, your data is not like sweeping up, it is just starting up, and on the bottom, you see your data is scooping down, and these particular points that you see in the bottom, or the tail part as we call it, is where there is a lot of information that you can access. And with respect to platykurtic, it's simple. As you can see, it's not something which is very elongated to the top and goes down. It's a very small curve. Eventually, this is still normally distributed. So what can these three types of kurtosis tell us? First of all, let's understand the middle curve, which is mesokurtic. When we say a curve is mesokurtic, what we're trying to say is the kurtosis is zero at that point of time, or the kurtosis at that very point of time. When we speak about how data can vary in those points, it is very, very similar to being zero. It means data is normally distributed, and eventually if your data is normally distributed, it will always follow the mesokurtic pattern. Okay, mesokurtic is the regular case. Now, what about leptokurtic? Leptokurtic is a very steep curve that goes up and down. Here we'll say that there is positive kurtosis, because tail on the both sides, as you can see, there's a quick heavy ascent and there's a quick heavy descent that is happening, right? So if your curve tail is very, very heavy, there are certain values there is the reason your curve looks like that. Since there are values there, it means that both the side of your tails have some important data that you have mapped. It is very far away from the mean, it is very far away from the median, it is very far away from the mode. When that is the case, what do we call these values? We call them as outliers. Outliers are these couple of cases which are very, very different from the other cases. Now, if I ask you saying, hey, what is your blood pressure? Or let's take a simple example. What is your age? You can tell me a number between 1 and maybe 100, right? On an average case. Now, instead of maybe I say, hey, type it down. Now, some of you might make a mistake while typing it down. Instead of you guys saying I am 25 years old, you might say I am 250 years old or 2,500 years old. So when you're manually doing this, it's easy to catch and say, hey, that's not in the range we're discussing. But when you have millions of values that you're trying to assess, you will just have to plot a curve like this to eventually tell you that, hey, someone has probably made a mistake here. Why is the, maybe even sales data, why is the sales data so low, or why is the sales data so high for this particular product? Sometimes it can be outliers. A product you're selling for $10 today, tomorrow you can sell it for $100. That means that the 100 is going to sit somewhere on the right side of your curve, where the average sale of your product is maybe $50. That is in the middle. The mean, the median, the mode is equal, right? So if it is leptokurtic, one important thing you have to assess and analyze is that you will have a lot of outliers. When you have a lot of outliers, especially in financial analytics, if there is someone who is applying for a loan and their pattern is considered to be leptocutic, it means that this person might not fulfill the loan if the bank gives the loan. That is where they can say we can decline your loan, right? We don't want to provide the loan. So if there's a lot of outliers, especially on the negative side or especially on the positive side, it says that there is something wrong with the data that they have at the hand. Fantastic. Mesocutic done, leptocutic done. What about platycutic? Platycutic indicates that there is certain negative kurtosis. It means that your tails are very much flat, right? See, platycutic has a tail which is only slight angle that goes up and down. This is like a very tiny hill that is maybe next to your house. Mesocutic is maybe something like the Western Ghats. Leptocutic is something like the Himalayas, right? So think about that. And here, once we see that the tails are flat on both sides, it means that all of these data elements, there is no steep change that is happening between your data points. It means that yes, even though it is only this much of data that we have, even though it's only small amount of variability that we have, at the end of the day, you're still seeing that there is very less amount of outliers. So especially in the domain of finances, especially in provision of loan, especially if analyzing if someone will fulfill a loan or not, their curve, if it's platycutic, it means that this person has always had a good track record and that this person can actually go on to fulfill the loan. It's not just loan. Whenever someone is trying to invest in a stock or a share or something, they try to see what is the share price, stock price, and once you analyze it in the form of a distribution, you will understand this is what everyone is after. There shouldn't be any rapid surges, right? I'm not talking directly in terms of price. I'm talking in terms of variability with respect to a standard that is set, with respect to an average price that is set, right? So guys, it is very important at this moment of time that you understand leptocutic, you understand mesocutic, and you understand the platycutic, right? All these are fantastic types of kurtosis. On the whole, we just explained the concept to you, but you have to understand these concepts are at the heart. They are literally at the foundation for you guys to build your descriptive statistics abilities on. Well guys, with this, we have come to the end of this course. Let me quickly summarize everything that we have learned. At the start, we considered multiple examples to show we have used statistics in real world previously, which we may not know that we have done so. After having an introduction to statistics, we understood what it is in its theoretical fashion. We understood it with even more examples. Once we understood what statistics is, we were curious about how we can use data. Once we were curious about how we can use data, we had to understand what are the various types of data that we can use in multiple ways. So we took a look at all of that. Once we cleared the various types of data, you were asking a question, okay, now we know the type of data. How do we go on to perform analysis? So we took a look at the various types of statistical analysis that you could perform as well. Once we were cleared with that, once we understood what inferential statistics is, once we understood what descriptive statistics is, we dive right into the heart of the measures, measure of central tendency, measures of variability, measures of relationships, measures of skewness, and even kurtosis, right? So all of these concepts will help you get a look at your data, which is almost impossible to have a similar look at it if you just take a look at it with the naked eye, right? So all of these concepts that we have discussed are super important in the real world as well. So if you're a person, if you're looking forward to become a statistician, if you're looking forward to be a person who will be performing a lot of analysis, this is the data that you will be using. This is the foundation through which you'll be using the same concepts on multiple complex data sets that are out there, right? Well guys, with this, we have come to the end of the course. I hope everything that I've covered in this course is clear to all of you all. On that note, thank you so much for completing this course. I'll see you again on the next one. My name is Anirudh Rao. Have a nice day ahead.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.